Oh, and now we do have everybody, just as I'm starting recording. Okay. Actually, I'm going to shut some applications down here. Okay. Okay. So, well, this is our last class meeting. Wish I could say the same for PDEs, but I'll take what we can get. So, if anyone wants to ask homework questions during this class period next week on Monday and Wednesday, I'm fine with doing that. I mean, I'll be available to do that, but I prefer if you let me know in advance if you're going to do that. I don't want to have a situation where I just am sitting here by myself in Teams and nobody comes. So, because we all have a lot going on, myself included, and if I know that no one is going to come, then certainly other things that can be done at that time, like grading your stuff. Okay. Another item is this is for master students, which actually, most of you are, or maybe all of you are. Oh, I think so. Okay, so non-thesis students are required to take 3 comprehensive exams. Thesis students take 2, and they have to come from different areas. So this class 610 falls under the numerical analysis area. There's also differential equations with ordinary and partial. There's real analysis, and then there's algebra, which includes modern algebra, number theory, and that sort of thing. So if anyone would like to take the comprehensive exam for this class, I do have an exam that I give for it, because we don't have a exam for the class. Normally, it's all homework, but I can give a comprehensive exam. So if you'd like to do that, please let me know. As the semester winds down, I'm going to be around until Monday, May 10th, which is the day that grades are due. I'll have to figure things out as far as the logistics of administering it and so forth, and um, consistent with whatever faculty members do. And I can tell you that the exam would be based on non-MATLAB homework problems. So it would be a written exam like you'd get in any ever class. Um, so if you were to study those problems, then you'd be in great shape for it. So, um, if you'd like to do that exam, um, I need to hear from you. So please let me know. Um, okay. Let's see. Okay. Oh, hold on a second. Sorry, I need to figure something out here real quick. Okay. Okay, sorry. Let me get the screen share going. All right. So continuing where I left off last time with tiptoeing into statistical learning. So this corresponds to 2.2 of the free textbook that I that I posted, showed a link to last time, and also I'm going to be talking about principal component analysis, and so this is my source for what I'm covering about that. Okay. So as far as assessing the accuracy of a model that we construct, if you're trying to model some function, unknown function f of x, and you have some approximation f hat of x, like I was talking about last time, how can we analyze the accuracy of f hat? Okay, so and that doesn't think of anything else. There is no one approach that's ideal for all problems. That it just depends on what kind of data you have. What kind of how do x and y relate to one another? What is it sort of a situation where you could use polynomial fitting, or would not work well in this case? And in spite of that, that we do have some general principles that we can follow that can provide some guidance in selecting a method or determining that maybe a certain method is not a good way to go. So key concept here is called quality of fit. All right, so we have our function f hat that's meant to approximate our unknown function f. And if we have, so if we're performing supervised learning where we have some data, some xy values to consider, then we can substitute our x values into our approximate f and compare with the corresponding y values. And then we have a mean square error here, which so since we're having the sum of squares of the deviations divided by n, this is similar to the notion of definition of population variance as opposed to sample variance. Okay. Now, there are two kinds of mean squared error, or MSE. There's that for the training data. So that's some given data that you use to develop f hat in the first place. As opposed to test mean square error, and that deals with x and y values that are not included in the training data. Now, this it's so if it's a test MSE, that's what you want to be small because you're using certain given data to develop your model, and then you're going to try it out on other XY pairs, and hope that it produces a that is accurate for those as well. So this is the goal, is to minimize this. Okay. All right. Now, the way we construct f hat, that's intended to minimize the training MSE, and then we're just crossing our fingers and hoping that the test MSE will also be small. But that's not necessarily going to happen, unfortunately. Okay. But it's a test MSE that determines how well f hat's going to work for the tasks that I mentioned last time, prediction and inference. So if you make your model more flexible, then you can make training MSE as small as you want. Like let's suppose that the training data has a roughly linear relationship, and you can use the least squares line that passes through those points. But if a relationship is not really linear, then you might choose a more flexible model, like allowing a higher degree polynomial. And of course, what you could do is if you allow a degree of a polynomial to be high enough, you can exactly fit all the training data, and you can drive this training MSE down to 0. You can always do it, because that's an example of what I referred to last time as reducible error. But if you do that, that leads to what I just mentioned last time, overfitting. That you're picking up you're not fitting not just the data, but also any noise or error in the data, and that's going to drive your test MSE up. So don't focus too much on trying to minimize training MSE. You're sacrificing test MSE, which is what you're really trying to make small. So we actually have a trade-off going here. Okay, that if you were to graph the test MSE as a function of model flexibility, so like for example, let's suppose you can easily quantify model flexibility in terms of, like for example, a degree of polynomial fit, if you want to restrict yourself to polynomials, or how many parameters that you're using to fit your data. So these are all ways to measure model flexibility. What happens is a test MSE, if you were to graph it against model flexibility, it has a U shape. So what I mean by that is so as you start to make your model more flexible, then that does reduce the test MSE to a point. But then your model gets more and more complex. You start getting into that overfitting territory, and even though your training MSE is going down, your test MSE is going to start to go up again. So there is a certain sweet spot where the model is moderately flexible, and that produces the best result in terms of minimizing test MSE. Now, if you have testing data available, then what you can do is you can just try them out. Try your model out on the test MSE. So this is data that is not included in your training data, and maybe tweak your model flexibility according to what works well. And then you're going to try that out on other data sets. But at least if you have some test data available, that can give you some confidence that your model works well. But often you don't have any test data available. So what can you do instead? You're not out of luck in that case. You can use cross-validation, using the training data to try to reduce the possibility of overfitting. Because if you remove some data from a training set, then it's still technically a different data set, even if you are incorporating that into your model. So an example of this that's very widely used is leave one out cross-validation. So that's an approach to help you help ensure a workable model that can hopefully keep test MSE low, even if you don't have test data available. Now, so we have this trade-off between small test MSE and training MSE. But in that case, the priority is still clear. It's test MSE that you want to reduce, and it's definitely a good idea to reduce model flexibility to a certain extent. Allow larger training MSE if it'll reduce your test MSE. But here's another trade-off, the bias variance trade-off. It's also important to consider in model development. Okay, so here we have the expected value of test MSE. So why a pair y naught x naught is part of your test data, or it's anything outside of your training data that you would plug into your approximate f. And what we can do is decompose this expected value of the test MSE as follows. So we get the variance of f hat, variance of our error epsilon, because remember at the very, very beginning, the last time, I had y is the true f of x, it's unknown, plus some error that's also unknown, but it's assumed to have a mean of 0. So there's always some uncertainty there. And then we have this term, the that's of a bias. So the variance in f hat is defined as follows. So it's the expected value of f hat squared minus the square applied to the expected value of f hat. And then this difference, so the expected value of f hat minus the true value of f, that would be the that's the bias. Okay. All right. Okay. And keep in mind that f of x naught dang it. But that would be y naught. Okay. Now, okay. So if f hat is to be effective, we can't do anything about this. That's like our irreducible error from last time. We need the variance to be small. We need the bias to be small. Now, to interpret these terms, when the variance is small, that means that the choice of training data does not really have a impact on our construction of f hat. That if we use different training data sets, that the f hat that is produced would be roughly the same. Now, what about bias? How do we interpret bias? Now, this goes to what type of function we use for f hat. Is it a polynomial? If so, of what degree? Or is it some other kind of function? So in that case, if we have low bias, that means that here we're accurately capturing the nature of a true unknown f. Okay. Now here's the problem. Models that are less flexible, like one of the least flexible of all, or is one of the simplest, like a linear model, just a least squares line, that does have a low variance because if you have a bunch of data and you have a least squares line that's passing through them, if you change just one of those values, it's generally not going to have a great impact on the slope and y-intercept of your least squares line, just because all of those points are having an impact. Now, if you use a more flexible model, like a higher degree polynomial, for instance, so that's going to have lower bias because it's going to fit the form of f more accurately. So either way, one of these is going to have low variance, one's going to have lower bias, and basically you're sacrificing one for the other. So reducing bias increases variance and vice versa. So again, we're looking for that sweet spot in terms of model flexibility to try to have the sum of variance and bias as small as possible. All right. So now, are any questions up to this point? And I can focus on something that ties much more closely to what we covered all semester long. That's principal component analysis, which is built on the singular value decomposition, the SVD. Okay. So what what principal component analysis does is a orthogonal linear transformation into a new coordinate system, so that the greatest variance by any projection of data lies in the first coordinate. That's the first principal component, and the second greatest variance in the second coordinate, and so on. But these coordinates really just correspond to the left singular vectors. So everything I'm describing here in this sentence is really just euphemisms for what you get from the SVD. And the variances themselves are actually the squares of the singular values. So now I'll flesh this out so you can see what I mean. But it's a nice application of the SVD besides the ones that we've seen already. So suppose we have a two-dimensional data set, and we're assuming that this data set has a zero mean. Now, to be more specific about that, what we have is a so we have this n by n matrix, and how we get that matrix is from our general data set. What we do is we subtract off this outer product. So U has the means of the rows of x naught, and then H is a vector of all ones. So this has the effect of, by subtracting off a row means, each row of x will have a zero mean. How do you get to row means? What you do is you're taking x naught and you're multiplying it by this vector of all ones. That has the effect of computing all the row sums. And then you divide by n, the number of columns. So the vector of U has the means of each row. So now, if I take this definition of U and substitute it in here, that's the same as subtracting this off. So what we have here, this is a projection matrix. HH transpose of rank 1. Okay. So by subtracting out the row means, each row of X has mean 0. Now, how to interpret X? So each column, what you're doing is you're performing an experiment. Each experiment generates a whole bunch of data. So you're performing the experiment n times. N is the number of columns. So each column is a different instance of that experiment. So whatever output you get from an experiment, that's what's reflected in your rows. So the rows correspond to particular items of output that you're getting from each experiment. So for example, suppose one of the pieces of data you're gathering is, let's say, temperature. Then maybe the first row of your matrix holds all the temperatures that were measured during each repetition of the experiment. And then all the other rows would represent other quantities that you're measuring. So now, from capital X, we take a singular value decomposition. All right, so here we have it. And yes, so notation's a little different. I had U before, U sigma V transpose, but now I have W. I mean, probably from the source that I used for principal component analysis that I mentioned earlier, but that's notation that they were using. But the meaning of everything is the same. So X is M by N. So this is M by M orthogonal. This is N by N orthogonal, and sigma's diagonal that has the singular values. W and V columns have the left and right singular vectors, respectively. Now, we know of the columns of W as the left singular vectors, but in this setting, they're also referred to as the principal components. Okay. So what we do is carry out what's called the Pca transformation. And all that means is we're just multiplying on the left by W transpose. So now we have this matrix that's just what's left of the SVD, because the W has been canceled out by orthogonality. So we just have sigma times V transpose. Okay. Now, what is this actually done? W is an orthogonal matrix. When you multiply by an orthogonal matrix, that's the effect of performing operations such as rotations and reflections. So really what we're doing is we're just taking, so each column of this matrix is a rotation of a corresponding column of X. So that's all we've done. We're taking the columns of X and rotated them. Now, rotating to what effect? So now in this matrix Y, our Pca transform, so the first row corresponds to scores in the cases of respect to the first principal component. So what that means is each row we're looking at how much the elements of that row depend on each component, W1, W2, etc. Because what's happening here is we're taking an inner product with each of the principal components. So the first row of this matrix, Y, represents the inner product or dot product of W1 with X. Yeah. Okay. All right, so more specifically, Yij is equal to of I transpose xj. Okay. All right. So now if I break down W and V into columns, so these are the left singular vectors, which are principal components, and these are right singular vectors. Okay. So what I could do is I can compress the data in X by multiplying, not by all of W transpose like I did before, but I can just take certain singular vectors, the first L. So now what I have here is, if I carry this out, since I'm only taking part of W, I'm only going to get part of sigma, like a largest L singular values, and then the corresponding right singular vectors. Now, we've seen this before. This is the best rank L approximation of X. And so that just comes from retaining only the first L singular values, effectively setting all our singular values to 0. So we're tossing the rest out. All right. Oh, dang it. Sorry, something went wrong here in my editor. Now I can't really see what I'm doing. I hate when this happens. I can never remember how to deal with it. Okay. Now it's too big. Okay. Now, to try to interpret this, let's suppose that if the columns of X are points in Rm, and we're going to assume that M is greater than or equal to N. So this is a rectangular matrix. Think of it as like a tall, thin matrix. Okay. Now, if we think of a first principal component, so this is a left singular vector corresponding to the largest singular value. So if we think of it as a line that has this direction that passes through the origin. Now remember, X is said to have all of its row means equal to 0. So the multidimensional mean of the data is the origin. So the interpretation of this leading principal component, or first principal component, is it is the line that is closest to all the points represented by X. So, for example, let's suppose that the largest singular value, so sigma 1, suppose it was much larger than all the others. Like we have this one dominant singular value. What we would find is that most of the points represented by X would be very close to this line. But in general case, if we had to try to describe all the data in X by a single line, the line of this direction, the first left singular vector, is the one that would come closest. Now, to show this, I can use this formula. This is something that normally taught in calculus, the distance from a point P to a line that has this vector equation. So we have this initial point, and then we have a parameter t in this direction. So the distance, the shortest distance from the point to the line is given by this formula here. So now I want to apply this to this situation with this line. So in our case, R0 would be 0 of the origin, and then V would be W1. So that's what I would be filling in here. And also P, in this case, would be one of the columns of X, because we're thinking of the columns of X as points in m-dimensional space. So if I substitute all those things in to this distance formula, so like I said, R0 is 0, P is a column of capital X. So that's XEJ, where EJ is a column of identity, J column of identity. Here V is W1. So then I start working all this out. So I replace X by its singular value decomposition here and here. And then the 2 norm, here we have a vector 2 norm. Well, that is not affected by multiplying on the left by an orthogonal matrix. So I multiply by W transpose. So we get some cancellation here. W1 is the first column of W. This is capital W E1. So that gives me an E1 here. And similarly here we have a E1 transpose. Now, sigma is a diagonal matrix. If I work out this is a first column of identity transpose sigma, which is a diagonal matrix. But what it's going to give me is a row vector that's all zeros except for sigma 1 in the first position. So now I had to have this number, sigma 1, I can move it out here. This is the same as VE1 transpose, using that oft-repeated property. Transpose of a product is a product of a transpose in reverse order. So this is just the first column of V transpose. And then by taking a dot product with EJ, that's just going to give me the row J column 1 element of V. Okay. Now, all right. I need to work this out a little bit more so you can see what's happening here. Because what's happening over here? Here we have diagonal matrix sigma times each times the this is a jth column of V transpose. So all of this is going to be a vector. And if I work out what this vector is, then each element of that vector is scaled by the corresponding singular value. Okay. So if I work out what that vector is, all right. This is going to be kind of freaky from a LaTeX point of view. All right, so this second term will be the same. All right. Oh, and actually, this is an element of an entry of a matrix, so that should not be bold. So, whoops. Okay. So what I have here is a vector. I need to describe what that vector is. And since I'm taking a column of a matrix, it's going to be a column vector. So the first element will be sigma 1. And then I'm taking, this is the row 1 column J element of V transpose, but that's the same as VJ1. Oh, sorry to fix that same formatting over here. Okay. Second element of this vector would be sigma 2 VJ2, because it's going to be because it's going to be a second element of column J of V transpose. So V transpose 2J, but that's the same as VJ2, and so on, all the way down to sigma NVJN. Okay. All right. Now, this vector is the vector that, remember, E1 is all 0 except for 1 in the first position. So this is a vector that is all 0 except for sigma 1 Vj1 is the first element. So this will cancel with this. And what's left is all the rest of the elements. And remember, the 2 norm of a vector is the squared is the sum of squares of all the elements. And that's what I have here. So summing up all of these guys, only from 2 to n, because the first one's canceled. So what does this mean? That the distance from the jth point to the line with direction W1 is given by this. So now what I want to do is I want to sum up these distances. I want to add up all the distances squared from the jth point to this line with direction W1. Well, first, any questions up to this point? I know a lot happened on this page. Actually, I'm going to make a note here that for this step, keep in mind that W1 is the same as W E1. And this is something that's important to be used to, that to extract a column of a matrix, you multiply by a column of identity. And substituting this in here, keeping in mind that W is an orthogonal matrix, that makes it easier to see how you get from this step to this one. So now if I take the sum of squares of all of those distances that I computed up above, so I've just filled that in here. So then I switch the orders of the summations. So then the sigma k of v should be squared. Whoops. Okay. So those could be pulled out of the sum over j. But what do we have here? This is the sum of squares of all the elements of column K of the matrix V. Remember, V is an orthogonal matrix. So if I can express this sum of squares as the 2 norm squared of column K of V, but because capital V is an orthogonal matrix, its rows and columns must be unit vectors. So this right here is just 1. So now this is what we get. It's the sum of squares of all the singular values except the first one. Okay. Now, I bring back some old material here. Recall the Frobenius norm is a square root of sum of squares of all the entries of a matrix, but it's also the square root of the sum of squares of all the singular values. Here, what I'm doing here, I'm taking a I'm subtracting off the component of x in the direction of W1. And okay. Wait, hold on a second. Okay. And this can be shown to be equal to Frobenius norm squared minus the 2 norm squared, because remember, 2 norm of a matrix is its largest singular value. But okay. Actually, probably the easiest way to see this. Okay. Okay. If I express this in terms of its SVD, so X is W sigma V transpose. And then I do that here too. But like the 2 norm, the Frobenius norm is invariant under orthogonal transformations. So W1, remember that is WE1. So I can incorporate that in here. So, well, this W transpose W, okay, I'll just copy and paste this. All right. Those cancel because W is orthogonal. Because the Frobenius norm is invariant under an orthogonal transformation on either side, I can multiply on the left by W transpose, and I can multiply on the right by V and cancel those. Okay. So now all that's left is sigma is a diagonal matrix. And then this right here, E1 transpose, that is an outer product. So this is a matrix that is all zeros except for the 1, 1 entry. So here we have all the diagonal matrix of all the singular values. Here we have a diagonal matrix that consists of only the first singular value, which will cancel with sigma 1 over here. So that would be equal to sum from 2 to n. Okay. But remember, the Frobenius norm comes from sum squares of all singular values. 2 norm comes from just the first one. So that's how it turns out to be equal to this. Now, but the key point to make here is, so W1, that's a unique direction that minimizes this quantity here, which we know because this is the error in a rank 1 approximation of x. And the way to get the best rank 1 approximation of x is to use the first or left singular vector. So in fact, if I fill this in here, then this is what we get. This is the best rank 1 approximation. So using W1 for our direction here makes this error as small as possible. This is the smallest it can get, just because it's been proven that this is the best rank 1 approximation. And the thing is, this is the error that we get by trying to find the unique line that comes as close as possible to all the points in X, by minimizing the sum of squares of the distance between those points and this line. And that's why W1 is the first principal component. All right, so what if we subtract out all the contributions to X from W1, like we start working with this, then the leading principal component of this matrix would be W2. And then the error would be the sum from k equals 3 to n of all the remaining singular values squared, and so on. Now, it turns out the singular values we've known from before, those are square roots of the eigenvalues of this matrix, XX transpose. But this is also known as a covariance matrix. So, and then this is a way of interpreting those singular values squared in terms of the portion of variance that is correlated with each eigenvector, because these are eigenvectors of XX transpose, as well as being the left singular vectors. All right. So really, this is what all PCA is doing. It just rotates the data points described by X so that they align with the principal components. All right. Okay. And the thing is, if you have certain singular values that are dominant, then those first few principal components might do a very good job of describing all of the data that you have. So then you can focus just on those few and work with a low rank approximation instead of the entire matrix X. All right. So this is useful for dimension reduction or data compression, but that's all of this is exactly what we saw earlier when covering the SVD. It's just low rank approximation, just by a different name. This is what happens often in this kind of setting, dealing with statistical learning and so forth, is a lot of these concepts that we're seeing in statistical learning are ones that are already covered in ordinary numerical analysis literature. It's just given a different name, but it's important to see that it really is the same thing. Okay. All All right. Now, drawbacks of principal component analysis. It is sensitive to how the variables are scaled. So, for example, suppose you have two variables, they have the same sample variance, positively correlated, then Pca would just be a rotation by 45 degrees. So the components will be seen as like equal in weight. But then if you take a first variable, you scale all of those by 100, then that one component becomes dominant. And the thing is that's something that can be misleading. So when you have variables of different units, Pca might skew the results one way or another. So it's very sensitive to the units that are given to the data that you have. Now, you can help the situation, like if you scale each variable so that it has unit variance, then that can remove this tendency to favor variables that are scaled higher. But this is why some people resort to alternatives to Pca to try to figure out what is the most significant part of a data that you have. And that's all it's about. This is trying to get to the heart of the matter, like what is influencing the results the most. Okay. Now, I've come to the end. So this is material that you can fall back on for the fifth and final quiz on statistical learning, and also consult the textbook posted on my site for more information. But this is just an idea of what goes on in that area. But also a very narrow view, since I just took some portions of a second chapter just to put some fundamental terminology out there and give an illustration of how this relates to concepts that we've seen earlier. Okay, so at this point, if you have any questions, let me know, whether it's about this or homework. Again, if you're interested in doing the comprehensive exam for this class, let me know so we can figure out the logistics on that. Okay. Well, I say we have a particularly quiet bunch today, or maybe we're just all toast. So I'll just end the recording here. So good luck finishing all the things.